So, there's been quite a few topics that we've covered for this test. Solving quadratic equations by factoring. So for that, we start with the quadratic equation. We get it into standard form, which means setting it equal to 0. Factor, set each factor equal to 0, and come up with our two solutions. We also worked with rational expressions. The domains had to do with thinking about what values would give us 0 in the denominator. Simplifying rational expressions, basically factoring and reducing. Multiplying and dividing rational expressions was a lot like simplifying, whereas adding and subtracting the rational expressions was a little more challenging because for those we had to come up with a least common denominator. Equations with rational expressions were where we could clear the fractions. The variations problems, direct variation, inverse variation, we had some story problems there. And then the complex numbers are the I values. So let's go through each of those a little bit. One thing that gets tricky on this test is it's very easy to look at a problem too quickly and start off on the wrong foot. So looking at these three problems, at first glance they look very familiar and very similar because they all have a similar rational expressions in them. But when you take a more careful look, I think you can see the difference. Here we have a rational expression where we're multiplying the two expressions together, and here we're adding. And then this one, we're actually have an equation rather than an expression because we've got that equal sign. So I'd like you to pause a minute and think about in your own words what it is you need to do with each of these problems. On this test, it's really, really crucial you first decide what it is you're looking at and what you're being asked to do with it before you do anything. The first step for each of those problems is significantly different for the different types of problems. What I recommend is when you sit down at the test, set your pencil aside, look through all the various problems. Then go back, pick up your pencil. Don't start the problems. Just write a note next to each problem, briefly saying in your own words what you're going to do. Do I need an LCD? Can I clear fractions? If you draw a blank, of course, just put a question mark next to it. Come back to it later. Don't worry about it. But only after you've got an outline for most of the problems should you actually start working the problems. I think you're going to find that'll help. Okay, so a few problems for review. Find the domain for the rational function, blah, blah, blah. So whenever we're being asked to find the domain, ignoring the rest of the problem for now, the domain what we're worrying about is dividing by 0. We don't want to divide by 0 because that's undefined. So what we want to do with this one is grab the denominator, x squared subtract 9, and we don't want that to equal 0. We can factor, it's a difference of squares. X plus 3x subtract 3. We do not want those factors to equal 0, so we don't want x plus 3 to equal 0, which tells us we don't want x to equal negative 3. We also do not want x subtract 3 to equal 0, so we do not want x to equal positive 3. So those are the restrictions on our domains. X can be any values except for those two values. Okay, next example here. Write each rational expression in lowest terms. So lowest terms means we need to reduce. So what we're going to do is factor the numerator and denominator, and if we're lucky, we're going to have some common factors that we can then reduce. So looking in the numerator, I've got a common 5, so I can factor out the 5. That leaves behind an x subtract 3. 5 times x is 5x, 5 times 3 is 15. In the denominator, looks like I can factor out a 25. 25 times x is 25x, and 25 times 3 is 75. So I can see the x subtract 3's are common, and then the 5 and the 25 would reduce because 25 is 5 times 5, leaving me with the rational expression 1/5. Okay, instructions for this one are just perform each indicated operation, write your answer in lowest terms. And we do have two very different problems here, even though they have the same directions. This one we have a division problem. With divisions, we do not need a common denominator, whereas this one, we have an addition problem. With addition problems, we need a common denominator. So I'll just write a note to myself here. Need LCD. And with the division, I want to remind myself to flip first, then multiply. So starting with the division problem, the first rational expression does not change. Only the one we're dividing by gets reversed or inverted. Once we've done that inverting, then we can think about factoring and hopefully again reducing. So I've got some greatest common factors here. I can factor 4 out of the numerator. X plus 2y over 3. The 9 is 3 times 3. And then I can factor a 5 out of the denominator, greatest common factor again, x plus 2y. Then I've got the fun part. Since it's now multiplication, it's all commutative, and so as long as I've got the same factor somewhere in the numerator as in the denominator, I can cancel them. So the x plus 2y jump right out at me. And then also I can reduce some 3's. That leaves me with a 12 up in the numerator and a 5 in the denominator. Okay. The next one, that's going to take a little more work because, again, I need a common denominator. And looking at the denominators, I can see they're actually pretty similar to each other. So there's not much I can do with x subtract 2. But here I can definitely factor 2 out. But I'm actually going to factor out a negative 2. That way I can reverse my signs here and have a positive x. And the negative 2 times the negative 2 would be the positive 4 I had there to begin with. And now I can see I've got an x subtract 2 common to both of these. So my LCD will be the x subtract 2 and the negative 2. So this one is ready to go. It's got the common denominator. I better write that down. LCD is negative 2 times x subtract 2. So this one's just missing the extra negative 2. So I'm going to multiply it, top and bottom, by negative 2. Give me negative 2 over negative 2x subtract 2. Resist the temptation to cancel. It is tempting because we were just doing that over here. But the reason we do not want to cancel is if we cancel now, we won't have a common denominator. And we need that common denominator because our next step then is to add these numerators. Negative 2 plus 1 is negative 1 over negative 2 x subtract 2. And I actually can do a little reducing here with the signs and make this a positive 1 over a positive 2 x subtract 2 for my final result. Okay, we've got another addition problem here. I'll go ahead and pause and let you take a try at that one. Well, did we get the same results? I factored my denominators and saw that I had 2 a subtract 1's and then another a plus 1. So my LCD, I wrote up here, a subtract 1 squared times a plus 1. So my first term here, I had the 2 a subtract 1's. It was missing the a plus 1, so I multiplied top and bottom by the a plus 1. This one I had the a plus 1, a subtract 1, but I need a second a subtract 1. So that got multiplied top and bottom here. That gave me my common denominator, so I could combine. And then I distributed in the numerator. Put everything over the LCD. 2a plus 3a is 5a. 2 subtract 3 is subtract 1 over the LCD for my final result. Again, your answers aren't particularly nice looking with these. That's just kind of the nature of the problem. The next one over here, though, we're actually going to get an answer. So the directions on this one are actually solve the equation, and we note that we do in fact have an equation because we've got that equal sign. The nice thing about solving equations, rather than adding or subtracting rational expressions, is we can actually clear out the fractions. So this one, the LCD is not too bad. It's just going to be the x squared. So we're going to multiply both sides of the equation by that x squared. which does mean distributing. On the right-hand side, 0 times x squared is still going to be 0, so be a little lazy there. So on the left side, we'll have a 3x squared. X squared times 5 over x, the x will cancel, leaving us just with the single x in the numerator. And the x squared cancels with the x squared here, and we have a subtract 2. And again, 0 times anything is still 0. Let's see, this is going to factor 3x and x. Let's see, with negative 2, how about if we did a subtract 2 here and a plus 1 here? Let's double check. 3x times x is 3x squared. 3x times negative 2 is a negative 6x. And 1 times x is a positive 1x. The negative 6x plus 1x would be negative 5x. And 1 times negative 2 is negative 2. Once it's factored, we can set each factor equal to 0. Solve. So we're getting x equals negative 1/3. And then over on this side, x equals 2. So we're getting two solutions. Neither of those solutions will give us 0 in the denominator. The only thing we'd have to worry about here on the domain is that we didn't get a solution of 0, which we did not. So we should have two valid solutions. Okay, so this one's a story problem, and it is a variation problem, as we can see with the varies, and in particular varies directly. So the surface area of a sphere varies directly as the square of its radius. Don't read beyond that at this point. I'll break these problems down, take it one piece at a time. So this is really giving us a general structure of the formula, the relationship between the area and the radius. So the surface area, I'll call that S, varies directly. So varies directly means it's going to be k times whatever it is we're working with. And here it's not just the radius, but the square of the radius. So k times r squared. Now we can take the next piece of information. If the surface area is 36 pi, when the radius is 3, and stop right there. Surface area is 36 pi when the radius is 3 inches. So putting in the 36 pi for S, putting in the 3 for the R, we're going to now solve for k. So this will give us 36 pi equals k. 3 squared is 9. Divide by the 9, and we get k is equal to 4 pi. So now our formula here has become, instead of S equals k times r squared, it's S equals 4 pi r squared. Now we're ready for the final question. Find the surface area S when the radius is 4. So the surface area is 4 pi times the radius squared, and we're being told the radius is 4. So 4 pi times 16, S equals, let's see, 24 carries, 64 pi, and looks like that's going to be square inches. And then complex numbers were the other topic on this test. So just be careful to pay attention to what operation, subtraction versus multiplication. So the multiplication ones we FOIL out, where the subtraction ones we simply gather like terms. Or same thing with the addition ones, we just simply gather like terms. But the subtraction ones, again, it's just easy to mess up a sign. So take the time to distribute that subtraction through before you combine like terms. And then we've got 3 subtract 5, and 2i plus I, so negative 2 plus 3i. Whereas if we've got 3 plus 2i times 5 subtract I, then we have to FOIL this out. So I have 3 times 5 for 15, 3 times negative I for negative 3i, 2i times 5 for 10i, 2i times negative I would be negative 2i squared. Don't miss the square there. Combining like terms, we've got 15i let's see, that would be a plus 7i. Subtract 2i squared is equal to negative 1. So we've got 15 plus 7i. Clean that up a little bit. Plus 7i. Subtract 2 times negative 1 is a plus 2. So 17 plus 7i. And this one here is a little bit tricky. You can use the formula for squaring, the a squared plus 2ab plus b squared, or you can write it out. This is 3 plus 2i times 3 plus 2i, and then FOIL it. Just do not, this is not going to equal 3 squared plus 2i squared. Don't do that. We've got to FOIL it out. We'll get 3 times 3 for 9, plus 3 times 2i for 6i, 3 times 2i for 6i, and then 2i times 2i would be plus 4i squared. So you'd lose these middle terms if you tried to do that shortcut. So that's why we don't get the correct answer if we do that. So that'd be 12i. And then I squared is negative 1. 4 times negative 1 would be negative 4. And 9 plus negative 4 would be 5 plus 12i. Okay, so most of these complex numbers, you're going to end up with something a plus bi, a plus bi, a plus bi. And then simplifying the square root of negative 50, that's just expanding it out. Let's see, 50 is 5 times 10. 10 is 5 times 2. And then times negative 1. So the 5 times 5, that's the square root of 25. Square root of 2 we're not going to be able to do anything with, and the square root of negative 1 by definition is I. So we get a 5, square root 2, and an I, or you can write that as 5i square root 2. Either one of those is fine with me.